IOE 413 Radiation Therapy Planning Study Guide. This question wants you to construct the matrix that converts beam weights into doses in the normal tissue voxels, that's A sub n, for this 3x3 arrangement of voxels. Now, let us assume, for this question, that vertical and horizontal beams lose 20% intensity for each voxel traversed. That is, each voxel absorbs 20% of the radiation beam, and 80% passes through. Beams along the diagonal lose 30% for each voxel traversed. That is, each voxel absorbs 30% of the radiation beam as it passes, and 70% continues on to the next voxel. The amount of radiation absorbed by voxel is the same for tumor and normal tissue voxels. Now that we have the assumptions in place, let's compute how much radiation is absorbed by each voxel. And let's start with the horizontal row here in the middle. And this row absorbs radiation from multiple beams. Let's look at normal voxel 4 to begin with. It absorbs radiation from beams 1 and 5. And the beam weights are W sub 1 and W sub 5. Let's figure out what is contributed by W sub 1. Okay? And it is going to be 20% of the weight of the radiation arriving at the edge of the voxel. What's arriving at the edge of the voxel is W sub 1. So by assumption, we absorb 0.2 times W sub 1. Okay? What's left at the edge of that voxel is going to be 0.8 W sub 1. And now the next voxel over gets 20% of what arrives at it, and what arrives at it is 0.8 W1, so we multiply 0.8 W1 by 0.2 to get 0.16 W1. And so what leaves at the edge of that voxel is 0.64 W1. And what is absorbed by tumor voxel 2 over here is going to be 20% of that amount. So 20% of 0.64 is 0.128, 0.128 of W sub 1. Okay? And that same pattern holds for example, this vertical column here, W sub 3, okay? Tumor voxel 3 would get 0.2 W sub 3. And then tumor voxel 1 would get 0.16 W sub 3. And then normal voxel 2 would get 0.128 W sub 3. Right, so that's sort of how it works for the horizontal and vertical. Now for the diagonals, let's consider, for example, W4. And we said that on the diagonal, we absorb 30% or 0.3 W sub 4. Okay? And then that leaves, exiting normal voxel 6, we end up with 0.7 W sub 4, which means that what's absorbed here is 0.3 or 30% of 0.7 W4. So when you multiply together 0.3 and 0.7, you get 0.21 W sub 4. And then what's exiting here, the edge of this voxel, is going to be 1 minus 0.3 minus 0.21, which is 0.49. So what you get here is 0.49 W sub 4. And then this voxel absorbs 30% of that. So we have 0.3 times 0.49, which is 0.147 times W sub 4. Okay? And that same pattern applies for all the other beams going along the diagonal. Okay? So we'll show you now with this how we can construct A sub n. Now let's make A sub n. We can do that first by considering normal voxel 4. normal voxel 4 corresponds to the fourth row of A sub n. Clearly, normal voxel 4 gets radiation from beam 1 and beam 5. And we've written down here that if, for example, you consider what radiation is coming in from beam 1, and the intensity before it hits any voxel is W sub 1, the amount of radiation that normal voxel 4 gets is 0.2. The next voxel is 0.16. The next one is 0.128. So clearly, the dose for normal voxel 4 gets 0.2 W1. We see that right there because the first column corresponds to W1. We don't get any radiation contribution from beams 2, 3, or 4. So that's why there's 0 there for 2, 3, and 4. And then beam 5, coming the other direction, is going to contribute 0.2 to that voxel, 0.16 to that voxel, and 0.128 to normal voxel 4, which is why we have 0.128 in the fifth column. And then beams 6, 7, and 8 contribute nothing to normal voxel 4, so we have 0, 0, 0 right there. Now let's move on to normal voxel 6, which is the sixth row. It gets radiation from beam 4 and beam 8. Now, the voxel that's most immediate to the application of beam 4 is going to get 0.3 times W sub 4. Okay, so let's look here at our fourth column and see that we have a 0.3 right there. And it's also going to accept radiation from beam 8, but beam 8 is going to have to pass through 2 diagonal voxels before getting to normal voxel 6. So the first voxel it passes through gets 0.3, the second 0.21, and then the third will be 0.147. So it will actually get 0.147 from beam 8, which is why we have a 0.147 in the 8th column. Now let's go back and consider normal voxel 1. Normal voxel 1 up here will get radiations from beams 8 and 4. Is most immediate to beam 8, so it will get 0.3 times beam 8. That's what we have over here in the 8th column. And W sub 4, beam 4, it comes in here, and we get 0.147 times W4 for our normal voxel 1. So what we end up with is for beam 4, we get a 0.147. And all the other beams don't even pass through this normal voxel 1, so we get zeros everywhere else. Let's look at normal voxel 2. That's the second row. It's right up here, normal voxel 2. It gets radiations from beams 3 and 7. So let's look at 7 first, because it is the most immediate voxel to beam 7. That is normal voxel 2 is the most immediate to the application of beam 7. And it's a vertical one, so we get a deposition of 0.2 times W7. Well, how do we represent that in here? We have 0.2 times W7 is represented as a 0.2 in the 7th column. Now let's see what beam 3 delivers. Well, it is attenuated by these first two voxels it goes through. So this voxel will get 0.2 times W3, and then 0.16 times W3, and then we get 0.128 times W3. And we see, in fact, that there's 0.128 in the third column. Now let's look at normal voxel 3. It gets radiation from beams 2 and 6, and clearly it's going to get 0.3 or 30% of W sub 6. So let's look down here and see that, oh, yep, in the 6th column we have 0.3. And then we also get radiation from W sub 2, but it has to traverse 2 diagonal voxels to get there. So by the time it's gone through 2 diagonal voxels, what it's contributing is 0.147. So you will note that we have a 0.147 for beam 2, right there in column 2. Let's look at the final voxel, normal voxel 5, the 5th row here in A sub n, and it's going to get 30% of W sub 2. Well, we see that right here because we have a 0.3 in the 2nd column. It's also going to get radiation from beam 6 coming the other direction. That's attenuated by these two diagonal voxels. So by the time it gets to normal voxel 5, it will be delivering 0.147. And so we see 0.147 in the 6th column, corresponding to beam W6.